welcome to this next unit of electrical machines 2. In last 3 units, what we actually did is this one, that we tried to find out the equivalent circuit of a transformer from circuit point of view, and from the concept of self and mutual inductances. You recall very quickly, I will tell that. So, this is two coupled coils having turns N 1 and N 2, and then when you pass some current through the coil, it produces flux. The direction of the flux can be obtained by wrapping your other fingers along the flow of the current, and thumb will give you the direction of the flux. So, phi. So, when you pass some current through a single coil, it produces fluxes which can be broken up into two parts. One is the flux component, which is confined to the core, that I call mutual flux, and the other flux which will be leakage flux, phi L 1. Suppose coil 1 carries current I 1, then inductance is defined as total flux linkage per unit ampere. So, phi M 1 plus phi L 1 by I 1 into N 1 gives you the inductance. This part of the inductance, which this flux completes its path through the air gap, and this flux causes an inductance of leakage inductance, which is L L 1, and this is L 1. In the same way, we did for L 2, and then I showed that M 2 1, I defined mutual inductance, and mutual inductance, whether you calculate it from coil 1 or from coil 2, it remains same. M 1 2 is equal to M 2 1, because reluctance of the common magnetic circuit is same. Then the important thing is, ultimately we showed that the self inductance of the coil in terms of mutual and leakage inductance comes out to be this L 1, and L 2 is like this. And finally, we wrote down the KVL equations on the two sides, remembering the fact how to put the dots on these two coils. Knowing those dots, I will be correctly writing the KVL equations with appropriate polarities of these voltages. Students often make confusion, but I hope you practice it, so that this will be no problem at all. And finally, we found out the equivalent circuit like this here. And is it not the same equivalent circuit we got from physical considerations of a transformer? See, R 1, and this is leakage reactance, this is the mutual inductance, which we denote by X m. But in terms of M, it is A into M, where A is the number of turns ratios N 1 by N 2. And all the impedances on the secondary side is reflected as A square into R 2, A square into omega L 2, and so on, A square into Z 2. I will just ask you to find out the equivalent circuit of the transformer referred to the secondary side. I leave it as an exercise to you, that is how this equivalent circuit will look like if I want to draw it with respect to the side 2. Anyway, so we spent some time on this, but I just thought that talking about self inductance and mutual inductance, some 2-3 important points, it is better I also say that. I am talking about L 1, L 2 M, and then without talking about energy storage and the relationship of L 1, L 2 in terms of M, it remains somewhat incomplete. So, what first I will do is this: recall that these are the two coils, okay, having inductances L 1, L 2, and this is the mutual inductance M. And we know that M is equal to, say, M is equal to, I can write as N 2 phi M 1 by I 1, and this M is also same as N 1 phi M 2 by I 2, when the first coil is carrying some current, flux linkage per unit ampere, and so on. Now, this fluxes, which is mutual flux here, this is phi m, and these are the leakage flux path phi l. Generally, if the coils are very tightly coupled, then leakage flux will be little. In fact, for a transformer, coupling should be made very high, so that most of the fluxes are mutual fluxes. And recall that L 1 was defined as N 1 into phi T 1. What is phi T 1? Total flux, sum of leakage and mutual flux, phi L and phi M, divided by I 1, and L 2 was denoted by N 2 phi T 2 divided by I 2. Now, this mutual flux can be expressed, suppose let phi M 1 is K 1 into phi T 1. Out of the total flux, what percentage is your mutual flux? For a transformer, it could be 98%, 97% of the total flux, leakage flux is little. So, K 1 represents that. Similarly, phi M 2 is K 2 into phi T 2. Now, what I do with these two equations, you just multiply them, so that it becomes m square into N 2 phi M 1 by I 1 into N 1 phi M 2 by I 2. Now, you just rearrange the not rearrange. Now, what you do for phi M 1, it is certain percentage of total flux phi T 1 by I 1 into N 1 phi M 2 is K 2 phi T 2 by I 2, is not. Then you write it in this way, K 1 K 2 you take, and then you write it, these terms can be arranged such that it is like this, that is, you take phi T 1 N 1 together, and then N 2 phi T 2 by I 2. But this is nothing but self inductance. So, K 1 K 2 into L 1 and L 2. This is L 1 and this term is L 2. So, m square is this one, and this K 1 into K 2 is called coefficient of coupling, not really that. So, K 1 m then will be K 1 K 2 square root of that and square root of that. Now, this is expressed as K into root over L 1 L 2. So, K is called the coefficient of coupling. Which is equal to root over K 1 K 2. What is K 1 K 2? K 1 is the how much of this total flux, it is a number, fraction, maybe 0.95, 0.98 for a very tightly coupled coil, and if its value is small, it means it is weakly coupled coil. If it is 0.5, that means 50% is mutual flux and 50% is leakage flux. Anyway, so this is a relationship which one should know when one is talking about the self and mutual inductances. The second thing I thought I must touch upon is the energy storage. In a mutually coupled coil, it will take few steps. Energy storage in coupled coils. The thing is, if we have a single coil and it has got self inductance L 1, and this is, suppose you are passing some current I 1 through it, I, because no point in telling about L 1, L 2. Suppose a single coil, it has got a inductance cell, and when it carries a current I, we know that energy storage is half L I square, so much joules, provided L is in Henry, I is in ampere, and this is denoted by this. Okay. So, this is the, and how do you get it? Very simply, it is like this. Since this is L, this is I. So, as I told you, it is better to represent this as a voltage drop in this way. L d I dt is the voltage, is not, and here is your say supply voltage, which causes this current to flow in this way. Now, as you can see, with respect to source, current is leaving the positive terminal. So, energy or power is supplied by the source, and instantaneous power supplied is V into I. Okay. Similarly, when you come to this inductor whose terminals are A and B here, this is also A and B. The polarity of the voltage across the inductor, this is plus, this is minus L d I dt, and current is entering through the positive terminal, means that it is absorbing power. So, source is delivering and it is absorbing. Now, power absorbed by L is dP is equal to voltage across it into the current I. Suppose in time dt, energy supplied, energy absorbed by L is, let us call it dW, and it will be L d I dt into I into dt. This dt you can cancel out because they are not equal to 0, but very small. So, L I d I. Therefore, if you are changing the current from say 0 ampere to some certain ampere I, it will be 0 to I d I, and that gives you half L I square, a very familiar results, you know that. Now, let us see what happens, how do you calculate the energy storage in a coupled coil. So, we take in the same way these two coils, suppose these are the dots, and here I will connect one source, and let us assume this coils has got negligible resistance, almost ideal coil. So, here you connect a source V 1 t, and current absorbed by this coil is I 1. Similarly, you imagine you have connected another source V 2 to here and its current direction is like this. You can choose the current direction in whichever direction you please, but I have just assumed like that I 2. Now, you see in this system, so these two coils are mutually coupled, having mutual inductance M and self inductances L 1 L 2. Now, to understand how energy is absorbed in it, what I will do? I will translate this diagram to, because between these 2 points there will be 2 sources of EMF. This is one, this is another. It will also help you to repeat those steps correctly. So, for example, here there will be one voltage plus minus, I 1 is this current. So, for self inductance, this is the source L d I dt, is not. Similarly, for the current in the second coil, there will be induced EMF here, and what will be the polarity? Through the dot it is entering. So, dot will become plus, that is the upper side. So, this is plus minus M d I 2 dt. In our earlier case, I assumed the supply source to be sinusoidal, and then what I did for d dt, you just replace it by j omega, then you will get L j omega I 1, this term, if the supply happens to be sinusoidal, but in time domain okay, this is fine. Polarity is like this. Similarly, for the second coil, there will be 2 sources, because between these 2 points self inductance exists and it has got a coupling with the first coil. So far as I 2 is this direction and this is your supply voltage, mind you, V 2 plus minus. So, I 2 is entering through, so this will be L 2 d I 2 dt self inductance, and plus mutual inductance will be M d I 1 dt. Now, we have to decide where to write plus minus. Now, see, through the first coil I 1 is entering through the dot, then because of mutually induced voltage in the second coil, it should be M d I 1 dt with upper side plus, that is the thing. So, once this is correctly drawn, then calculations of instantaneous power and from that energy becomes very simple. Why? See, there are now 2 sources, and so far as this part is concerned, current is entering through the positive here, power is absorbed, and about these 2 sources also power is being absorbed. Sources means they are inductances, coupled inductances. So, we write instantaneous power absorbed, mind you, absorbed, because both these coils are absorbing power. Who decides that? Because I have assumed the currents in such a direction, polarity of the voltage is given. So, I can make out whether this fellow is absorbing power or not. So, this is plus minus at the voltages, current is entering through the plus, it is absorbing. So we write instantaneous power will be then voltage across this coil, first coil, plus M d I 2 dt. This is the voltage between these 2 points into I 1. But this fellow also absorbs power. So, I have to also consider this coil, how much power it is absorbing. It is L 2 d I 2 dt plus m d I 1 dt and the current is I 2. This is the instantaneous power. So, both the sources are as if pumping power into the system. The system is L 1, L 2 and M. So, this is how it looks like. Then the energy absorbed in time dt, which is vanishingly small, that is calculus type dx dt, like that dt. So, it will be in that small time energy absorbed, let us write it as dw is equal to p dt. So, multiply with dt and cancel it out. So, it will be L 1 d I 1 plus m d I 2 into I 1 plus L 2 d I 2 plus m d I 1 into I 2. And this we can write it like this as L 1 I 1 d I 1 plus m I 1 d I 2 this term plus L 2 I 2 d I 2 this term and plus m I 2 d I 1. This way I can write. Now, these two terms can be grouped together. So, this is L 1 I 1 d I 1 and then let me write the second last term first, that is L 2 term L 2 I 2 d I 2 and then this one is m I 1 d I 2 plus I 2 d I 1, like this I can write. And so dw is L 1 I 1 d I 1 plus L 2 I 2 d I 2 and this thing, if you look at it carefully, this term I 1 d I 2 plus I 2 d I 2 can be written as d of I 1 I 2. So, energy supplied, energy stored when current changes from 0 to some current, say I 1 in coil 1 and 0 to I 2 in coil 2. In that a particular time interval, if current changes 0 to I 1 in coil 1, 0 to I 2 in coil 2, then total energy stored will be equal to L 1, this is 0 to I 1 d I 1 plus L 2 0 to I 2 d I 2 and plus m d of I 1 I 2. And what should be the limits? Limit should be 0 to I 1 I 2, because this is the differential thing. If it is dx, limit of x I 1 I 2. So, it was 0, I 1 I 2 was 0 initially, then finally, it has reached I 1 I 2. So, product. So, if you calculate this, it will be half L I 1 square plus half L 2 I 2 square and plus m into I 1 I 2. So, the energy stored in a coupled coils when it carries some current I 1 and I 2 is given by this. So, in this unit what I have done is I reviewed very briefly the last lecture. I will request you pause the videos of the last 3 units very carefully and try to understand the main points, that is how to tackle mutually coupled coils with confidence. And today what I have done in this unit is I just highlighted 2 things. One is about the coefficient of coupling, what does that mean, how they are related, that is m can be expressed as coefficient of coupling and L 1 L 2, that I have done. And to just complete this self mutual inductance, the energy from the energy point of view, I know that if a single inductor is carrying some current, it stores energy. What happens if it is a mutually coupled coils? How much energy will be stored in that? So, I found out that also, and remember to do this, these are the best way to do. Given 2 mutual coupled coils B 1 B 2, both the sides I am. So, these 2 sources are pumping power into the system. The way I have assumed currents and voltage polarities, it means that it is pumping energy. There is no resistance in the coil. Where that energy is going? That energy is being stored in the magnetic field. And how to get that? Whenever a coil is there, it can be represented by 2 sources. After all, flux linking is also taking place in the coil N d phi dt. So, some voltage is induced in the coil. This voltage is being balanced by the supply voltage, that is the thing. But when it is a mutually coupled coils, okay, I 1 wherever is entering, irrespective of the dot, plus will be which side I 1 is entering, that we know L 1 d I 1 dt. Now, here comes the importance of dot. If I 2 is going like this, m d I 2 dt will be definitely there, another source of EMF, but the polarity of that voltage will be through the dot I 2 is entering. Here also that dot will become plus, that is the upper side will become plus. Like that I drew this, and then instantaneous power, from instantaneous power you get elemental energy, integrate it appropriately to get the final energy stored expression. Thank you.